Okay, so you should have seen that on Brightspace I changed the deadline of the homework to Thursday. So did you start the homework? Any problems? Okay, that's good. So on Wednesday I will hold an office hour sometime around 7 p.m. on our Teams channel. So if you have any questions regarding the homework, you can contact me over there. All right, so we talked about this idea of the fugacity. You can think about it as a kind of a corrected pressure. It has the dimensions of pressure for real gas. And the idea was that we can write a very nice equation for the change in the Gibbs free energy of an ideal gas, molar Gibbs free energy of ideal gas at a constant temperature as a function of the pressure. And that gives us that RT, dl, and P. So we are motivated with that. And for a real gas, we define this change in the Gibbs free energy RT times dln of something that we call it fugacity. So as our gas approaches to the ideal case, that F parameter approaches to the pressure of the gas. So that's the idea. Then we saw we can subtract these two equations and write it in terms of the basically residual molar Gibbs free energy divided by RT, which is going to give us an equation to estimate the fugacity of a real gas. Okay, so why we are doing this? Because we can manage to understand what is the residual Gibbs free energy for a gas based on the equation of the state. So if we have that, then we can calculate the fugacity. So you have probably saw some examples in your first part of the thermo. So you had different equation of the states, and you could basically use them to calculate the fugacity. So the idea is I can write the G minus G ideal gas as basically the difference between the enthalpy and the entropic part, right? G is H minus Ts. So I can decompose that fraction in two parts, and using the relationships that we had for the basically change in the enthalpy and change in entropy, you can estimate, basically, you can actually calculate, not estimate, calculate exactly what is going to be ln F over P, okay? So that equation we have, basically the key part is the last one, right? So this is the relationship we are going to use when we have the pressure of the real gas as a function of the temperature. And this quantity in the parentheses also, F over P, which shows the ratio of the fugacity of the real gas to the ideal gas. It's always called a fugacity coefficient, so it's a dimensionless number. Okay. So if you have the equation of a state, so you can use that equation to calculate the fugacity or fugacity coefficient. So some equation of a state are a little bit difficult to work because you don't have the explicit relationship between the P and V very nicely written to put it in the integral. So there are different variations of this integral form. So you can write it in terms of the dP. So this is what you saw. If you have the Z for a gas, this is basically Z here is the PV divided by RT. It's the compressibility of a gas. You can replace it over there. For example, the second equation is good for the virial equation of a state. Third one, when you have the basically expression based on the volume, right? So this is based on the dV. So if you have expression of the equation of, say, using the volume equals to some function of the RTP, so you can use the last one. All right, so this was for gases. Then you learn how to estimate the fugacity of a liquid, right? Do you remember that? How did we do this? Do you remember the pointing correction? So the idea of the basic estimation of the fugacity of a liquid is that, so at a fixed temperature, so basically you have this equilibrium between the liquid, vapor, and for vapor, basically we call it as a saturation fugacity. So this side I can get it from the equation of state. So you remember, liquid is equilibrium in a vapor. So the fugacity of a vapor is going to be determined from your equation of the state, whatever equation of the state you have, right? Then, fugacity of a liquid that is out of equilibrium, let's say, so this is your equilibrium line, it's basically the saturation curve that you have. Then we are looking for finding the fugacity at a point like P, and basically temperature T, where your pressure is higher than the P saturation. So it is in the deep liquid state. So the estimation that we have, we say, okay, it's going to be equal to the vapor fugacity, which is the Fsat, times some correction. And the correction comes from the integration that we have basically at a constant temperature going from this point to this point, okay? So we can write the equations for the d ln f over p as a function of dp. So we haven't done anything significant over there. So if we replace that through the integration from p1 to p2, so let's call this as a state point 1 going to the state point 2. So you can have this basically relationships that shows the Gibbs free energy change going from 1 to 2, and you can estimate the point 1 using your saturation temperature and pressure. And at the end, what you are going to find, basically combining these two logarithmic terms over there that we have, the saturation and incorporating the saturation fugacity, your fugacity in the liquid state is just going to be, basically this is going to be your Poynting correction, right? So there's an exponential term that depends on the molar volume, the saturation pressure and temperature, and the departure from the saturation point that you have. So this is your delta P. That is the vertical line that we had it, right? So this is the saturation curve. State 1, you are going into the liquid. So that is your delta P, okay? So as long as I know that what is that delta P, so I can easily calculate that contribution coming from this basically liquid part and calculate the fugacity at the Psat and basically at the temperature that I have. Okay, so these were basically a few methods that we use in Thermo I to calculate the fugacity of the pure component. So that's the key point. So there is no mixture, so always we were dealing with one component, right? And now we are going to basically see how we can extend these methods to the system that they have multiple components in it, right? So briefly, in the part 1 of this class, so basically we are going to talk about the mixtures. You will see a lot of definition of parameters that correspond to the state of a mixture. We are going to talk about the ideal mixing. Okay, what is an ideal solution, ideal vapor, and introducing a little bit of non-ideality, what we mean with that. So that is basically your exam 1. Okay. In part 2, we are going to just focus on the non-ideal systems. Those are basically the real cases that we see a lot in lab and in industry. So we need to understand the physics behind them, how we can build theoretical frameworks, and use equation of states to calculate this basically phase equilibrium property. In part 3, we will basically take part 2 and apply the same principles that we have learned to different types of equilibriums. So in part 1 and 2, dominantly you're interested in vapor liquids equilibrium. In part 3, you're going to use that framework for different types, liquid, solid, right? Solid, doesn't matter. So you will see how basically powerful is this method, okay? Any questions? All right, let's get started. So, basically this part is the chapter 9 in your textbook. And few questions that we are going to consider here as our motivations. What are the properties of an ideal solution? What is an ideal solution? How do we call something that has more than one component as ideal solution? What do you think about it? What your intuition says?
Everything in the solution is like perfectly distributed. It's like no matter what part you take from the solution, it's always the same composition.
The same composition. That's a great answer. I like that. Then we are going to extend the idea of these thermodynamic variables that you have learned, like internal energy, entropy, enthalpy, to define it for a mixture. How do you define when you have component 1 and 2? Let's say you learn for component 1, you have one enthalpy, we call it molar enthalpy, right? Now you have component 2. And you have a mole fraction between component 1 and 2. I know 20% 1, 80% 2. What would be the mixture enthalpy, molar enthalpy? Is it going to be just the weighted average? Is it a weighted average? Then is it a molar average or mass-based average? Which one do you think? Which one?
I would think molar, just because we usually work with.
We usually work with molar. That makes more sense. Well, yeah, you are on the right track. You will see that. So, can we say for that entropy? Maybe, maybe not. I don't know. We'll figure it out. Then some new stuff you will learn. What are the partial molar properties? So this is specific for the mixtures. How we define mixture with more than one component, basically systems. And then we will establish some framework to quantify the molar contribution of components to the whole mixture. So this goes back to that first question about enthalpy of mixture, how we define it. And then we will take the same definitions to talk about the mixture that when we are dealing with the ideal gas. Okay, so first question I have here for you to think about, and it is in your book also. It's a typical question that we ask in phase equilibrium thermal. So you have 50 milliliter of water and same volume of ethane. Mix them together. Okay. So what is going to be the final volume of this mixture? I will give you 3 options. It's going to be exactly 100 milliliter, more than 100 or less than 100.
Exactly 100.
Exactly 100. So how many people agree with him?
Feels like a trap though. Makes sense.
It makes sense, right? Yeah, it makes sense. That's okay. Anybody who is not agreeing with him, that's fine. Don't be shy. Yeah?
Less than 100.
Less than 100. What was the reason for that?
I think they're miscible together, so do some interactions with the
Okay, yeah, you got it right. Yeah.
Tiny amount of ethanol will evaporate less than 100.
true.
Well, let's say there is no evaporation. Closed system, right? Closed system, no evaporation. You ensure that all of them are in the liquid state. Okay? All right, so what really happens here is that your mixture volume will be less than 100 milliliter. Okay? The reason is yes, because of the interaction, the size of these molecules that you have here. So this is water, and ethanol is something like this. They can create hydrogen bonds with each other. Water can go penetrate between the ethanol molecules that they basically can pack really efficiently. So I talked about two things, right? So hydrogen bonding, which comes from the interactions, right? And packing. That comes from the size and shape. So for this type of molecules that they have similar interactions and also similar size or shape, you would expect that this total volume that you are going to have is going to be less than what your intuition says, basically add them up. Okay. So in this case, it's going to be less than 100. So definitely V is less than 100. And this basically opens up the new concept here about ideal solution. The 100 milliliter that you said corresponds to the case that molecules are exactly like the same thing, right? So you add 20 milliliter of water, 80 milliliter of water, resulting basically liquid is going to be 100 milliliter. There is no difference between the components. So that's the ideal basically solution. So two main assumptions that we have for basically ideality. The molecules in the mixture, they need to have the same size and shape, and also the same type of interaction, exactly same type of interaction. So this is very important. So basically this talks about the entropic origin, and this is the enthalpic part. So whenever we are thinking about the mixing two things, there are two things that are fighting with each other, entropy versus enthalpy. And that's the definition of the Gibbs free energy. It is H minus Ts. The entropic part can be easily modulated by temperature. Right? So you can change the temperature to basically control that contribution that comes from the size and shape because of the dynamics of your system. So for ideal solution, when components are very similar to each other, for all the molar properties, what we can define is that I'm going to use this parameter M that basically stands for all the properties. It can be volume, enthalpy, it can be volume, entropy. So we will talk a little bit more about entropy. We need to be careful about that. Or Gibbs free energy, all the parameters that you know in the thermo. So I'm going to write them as the x1, which is the mole fraction of the component 1 in my mixture, times M1 ideal. Okay, so basically this M1 ideal basically for this case is just your molar property. There is a reason that we are using this type of definition. It's because of the entropy. We can talk about that. But in most cases, this M1 ideal that I have written is a molar property, molar volume. Let's say I'm going to write this equation for the ideal mixing volume that here. So V ideal is going to be X1, V1 plus X2, V2. And V1 and V2 are your molar volumes. That was basically that 100 milliliter, right? Exactly. Basically, volumes are additive in that case. Now, in a real mixture like water and ethanol, what you see, the real volume is different than what you expect from the additivity. So I can define another parameter. So excess volume. So for all of the parameters that we are going to consider, we can define this excess volume. So it shows the difference between the real molar volume and the ideal volume. Okay? So in the case of water and ethanol, what you saw over there when your volume was less than that 100 milliliter, your excess volume is negative or positive? Negative, right? Your volume has decreased. So if we look, so there is one example for water and ethanol. So the second example on the right-hand side is for acrylic esters and 1-hexanol. So if you look at the left plot here, so let me write it here. V excess is defined V minus V ideal. Yes.
So what's the difference between an excess property and residual?
Residual, it just focuses on the ideal gas. But I haven't put any definition. It's a pretty loose definition of the ideal mixture. And you will see ideal mixture is different from the ideal gas. That's a great question. So ideal gas is a very good reference point when you're thinking about vapor. Always we would like to define the differences between the property of a vapor with respect to the ideal gas. But ideal solution works good when we are dealing with liquids. So you will see that. Maybe middle of this or toward the end of the notes here. So this is the V excess minus V ideal. And obviously, when I'm plotting it versus the mole fraction of the ethanol, so this is the mole fraction of ethanol here. So it goes from 0 to 1. At two boundaries, what do I have? What is my mixture? When ethanol mole fraction is 0 or 1. When it is 1, it is pure ethanol, right? What is the excess volume over there?
0.
Does it make sense? It's a pure, right? So volume is additive at that point. So this is pure ethanol here. What is here? Pure water, right? And again, your excess volume is 0. So it means that volume is additive. Whatever composition you consider, so different curves corresponds to different pressure values here, and we are fixing the temperature at room temperature, 298 Kelvin, and you can see that always your excess volume basically is negative. So that's the basic take-home message for the water ethanol system. Okay, not always it is negative. Sometimes it can be positive too. So if you have 1-hexanol and acrylic esters mixed together, I'm not sure about the temperature over there for that graph, but let's say at the constant temperature that we have and different pressures that we can have, always the excess volume for the mixture case is positive. So positive can also happen. The physical reason behind is that maybe nanoscale phase segregation is happening, and these phases between component 1 and 2, basically they repel each other. Okay? So that's the reason for this, basically the positive excess volume that we have. Okay? To clearly understand to basically what's going on the nanoscale, you can do molecular dynamics simulation and basically look at the configuration, how these things have mixed. But usually what you see for those type of a liquid is that you have a small pockets of the component 1 and 2, which are basically repelling each other to give extra volume. Any questions? Okay. So now think about this example here. I'm going to pick components from the top row and see which one is close to ideal and which is non-ideal, right? So of course, if I get n-hexane, that's a pure component. It's an ideal. So let's focus on the second one, n-hexane, n-heptane. Do you think it is an ideal solution if I mix them together? Or they are non-ideal? Think about ideal here is that two things. Interaction should be similar to each other. Two, size and shape. First one and second one, I'm mixing them. Kind of, right?
Yeah, they're very close.
Okay, let's define one parameter here. I'm going to define an excess enthalpy. And the way that we are defining this is the mixture enthalpy minus the enthalpy of the ideal solution. Okay? Should be molar. So I mix them in the lab, I measure the enthalpy of my solution, that is H, that's the real enthalpy. Then I also know the pure component enthalpy, so I know how much I have put basically in my container, so I can calculate this excess enthalpy. For the first one, what is the excess enthalpy, by the way? 0, right? For the second one, this is very close to 0 actually, 0.46. Now, I'm going to mix n-hexane with 1-hexanol. What do you think about that? No, right? So the interactions are different. Although the size and shape are similar, I mean, effectively are the same, but interactions are different. And that's enough to give it to very high excess enthalpy, 460. So you can just get some scale of basically sense of the scale of these parameters, right? So the other one, n-hexane with cyclohexane. What about that? Size, shape, interactions.
I mean, the interactions are the same.
Same,
The
yeah.
size and shape.
Size and shapes are different, right? Size and shapes are different. So for this guy, the enthalpy of the mixture is 216, right? So basically, this shows you very high HXS, okay? It is difficult to say which one, basically size or interactions, dominates the contribution to your excess property. So you're going to do the experiment, or you do molecular dynamics simulation to calculate exactly that. But for our purposes, you should basically tell me that whether this is ideal or non-ideal. So that's what we are interested in. Okay? And you should be able to argue based on the size and shape. Yes.
Is there like a break point, or is it just vaguely low?
It is very vaguely defined, and that is partly because this ideal solution also is very vaguely defined. I mean, you can have different components, right? So it's still very close to the ideal solution. So there is no boundary to exactly define that. Okay, so let's see. Look at another example here. So So this is the example for ethanol and benzene. So you have the molar enthalpy of the liquid mixture. So this is for mixture. As a function of the mole fraction of ethanol. So, and you can see this basically non-ideal behavior. If it was ideal, you can have it at basically a line always at 0 as a function of mole fraction. Where are the pure enthalpy of benzene and ethanol on this curve? If you want to consider.
So what makes it most non-ideal at like 0.35 ethanol?
For these two components, not only the interactions are different, size, shape, mostly I think the interaction between the benzene rings, you have pi stacking happens over there for benzene.
Well, it's more, I would have thought that it would be the least ideal when it's half one and half the other. So why is it least ideal when it's 0.351
Yeah, okay,
and
yeah.
0.65 the other?
The non-ideality, or all of these parameters are not linearly basically correlated with the mole fraction. So this basically all of them have entropy origin. And entropy also is not linearly additive. So what you're assuming that you're putting two things together, you are basically considering the same share of the non-ideality between them, right? So that could be 50%. But when you have two different things, the number of the microstates that you are going to have for your system is not additive. So that's why you will see for entropy. But this comes from the entropic origin, that it is not exactly at 50%. But if you want to predict it as with a theory, it is just impossible to do that based on the theoretical framework. You need to do either experiment at the lab or in your computer running a molecular dynamics simulation type of things. Okay, one of the exercises in your book, so you have some experimental data for excess molar volume of acetone with 3 different normal alkanes at room temperature, N-hexane, N-heptane, and octane. So for all of them, we have basically excess volumes per centimeter cube per mole, and you can see as the chain length increases, you go from N-hexane to N-octane, the excess volume increases, right? Slightly increases. So what does it show? Increasing chain length of one of these components, okay, increases the degree of the non-ideality. So Vxs goes up, more non-ideal. Let's look at this one. Yeah, something like this you will see in your quiz next week on Tuesday. So we are going to have a quiz on chapter 9. Not the overview part, only what we have started to do. Okay, so water and N propane. I have the molecular structures for you over there. Ideal or non-ideal? Which one is more? Non-ideal, right? Why is that?
Oh, because the water is going to have different interactions.
Interaction. You know about the different interactions, right? Hydrophobic interactions that you have in the propane molecule versus the hydrogen bonding. That is very specific to water molecule and those systems that they have OH and the oxygen with the those pair of electrons, right? So for water and propane, the interaction is the key parameter here to make the system non-ideal. So it is non-ideal. What about N-hexane and benzene? It is non-ideal, right? What is the main reason for that?
Benzene is a different shape and it also
Shape.
has double bonds.
Yes, shape and also an energy that comes from also the shape, the geometry of the molecule, right? Benzene is pretty flat. It's a very flat molecule. It's different from cyclohexane. Cyclohexane has a 3D, basically, bonds, right? But benzene is just a flat. So that flatness gives it another type of interaction between these double bonds. They can stack on top of each other. Okay? So you have shape, you have the interaction. So this is also non-ideal. What about this guy? Orthoxylene and paraxylene. As long as they are liquid. Ideal? Yeah.
I'll say ideal, they're relatively similar. They're a singular spacing off.
Yeah.
I mean, there is a bit of stability difference between them, but I don't think that's enough to make it non.
Yep. Exactly. Okay, that's good enough for now. Those two things are very ideal when they are mixed as liquid. I'll show you when we are finishing this class. These two things, they have very different melting points. All right. So for ideal solution, always consider this idea of the size and shape plus interactions, then basically judge whether that mixture, two components or more than two components, always works based on that rule of thumb. Okay. All right, now let's do some calculations. So we have 1 liter of acetone, and we would like to make it a 50% by mass, a mixture of acetone as a component 1 and N-heptane as component 2. Okay. So the information I have also here is that the molar volume of the component 1, so I will give this to you, is 73.94 centimeter cube per mole. Molecular weight of the component 1, which is acetone, is 58.08 gram per mole. What else you need? So we want to basically find how much volume of N-heptane I need to add to this mixture to make it 50% by mass of acetone. So how should we proceed? And I will also give you this. So this is the V2 hat, 1.472 milliliter per gram. So this one is the specific volume of the N-heptane. Okay. Where should we start?
Find the mass weight of N-heptane.
Okay. So what principle you are using when you are saying that? It's the mass balance, right? So you start with the mass balance because mass is conserved. Volume is a little bit tricky. This is at least what we have learned so far. So, okay, so this is acetone here, so component 1. N-heptane. So M1, how much is the M1? Mass of the component 1 that we are putting into this weird mixer that we have here. So this is my big mixer, right? So I'm putting 2 components, mixing things together. How do you do it? I'm not looking for a number here, right?
We need the molar volume, the molar volume, because we know we have a liter of acetone,
So
so we need to know how many moles are in that.
do we have the molar volume of acetone here?
I don't think so.
V1, I have given you over there.
Oh, V1 right there.
Yeah.
There it is.
So since a centimeter cubed is just a liter, we can just take the.
Yeah. Yeah. So you have the basically amount of acetone here, right? So let's write it basically because I have it in mole, so we will go step by step. Let's not confuse ourselves. So I will calculate first a specific volume of the acetone. Okay, this is equivalent to that milliliter per gram. Then I can basically divide V by V hat. So this is going to give me 546 gram. Okay, now I know how much acetone I'm putting. That's the gram of acetone. I will wait and put it there. What else? Still we don't know how much volume we need for the N-heptane. What do you need here to calculate the volume of N-heptane?
The mass of N-heptane.
Do you really need molar mass of N-heptane here? I have given you the specific volume, right? So a specific volume can give you the total volume of the N-heptane, right? As long as you know what is the mass of the N-heptane. So can we calculate the mass of N-heptane here? How?
We have the specific volume, and we know their masses are equal.
Exactly, okay. So tell me how I can calculate the mass of the.
You just multiply the. Wait, what are we trying to find? The
Mass of the N-heptane. I want mass of N-heptane.
Oh, is it the same? Because it says it's the equal mass mixture.
Where did I say equal mass?
It's 50% by mass.
It's the 50% by mass. You have a mole fraction. Yeah, mass fraction. Yeah. Yeah.
So you're asking for the mass of N-heptane?
Yes. You need to find the mass of N-heptane, then convert it to the volume, right? If you write a mass balance, right? If you write just a simple mass balance, for component 1, right? Which is the acetone here. So it's going to be 785.546, right? This is grams that I have. M2 doesn't have any acetone in it, right? So that there is no acetone over there. It's just N-heptane. Two different streams are coming. Then in the M3 is the total mass I have. So it's going to be M3 times, it is 50%. So I can calculate M3. Right? Total mass of the mixture that I have. Okay, can I calculate how much is the mass of the N-heptane? Considering that there is no chemical reaction or something weird or evaporation is happening, right? Because the overall mass balance M1 plus M2 is M3. So M2 is going to be 785.546 gram, right? So this is the mass of N-heptane. Does it make sense? So how can I get the volume now? So this is the information you have. You have the specific volume of N-heptane. You have the mass of N-heptane, right? Then
Is the interactions between molecules large enough to change the overall volume to the point where it matters?
So we'll get back to this. That's it.
Because last time you asked this question.
Yeah. But we are just using the conservation of mass here, right? So it doesn't change the specific volume of the, right? So it's okay to use basically, this is the relationship that we have, right? So this is the definition of the specific basically volume of the N-heptane here, right? So using this, the volume of N-heptane is going to be M2 times we had 2, so it's going to be milliliter. So your total volume of this mixture, now I'm adding things together. If I calculate using this, it's going to be 2156 milliliter. This is just a volume additivity, so I'm adding the two volumes, right? So considering it as an ideal when I'm writing that part. If you go into the lab and basically measure the volume, okay, measure the actual total volume for this particular experiment, it's going to be 22 milliliter. So slightly, your actual basically volume is larger than just what you get from the volume additivity. But for calculating basically the mass, those things, then you can use conservation of mass. That's universal. So there shouldn't be any problem with that. So we'll talk a little bit more later. So there's also one very nice example in your textbook, which I like it a lot. It's the same concept. Basically talks about the solution enthalpy, how we can basically utilize the enthalpy curves to calculate this properties of mixture. So we have Again, a mixing process. One stream is a pure benzene. 10 mole per second comes in at temperature of 308, and it is mixed with another stream of basically mixture of benzene and 2-propanol, which is 20% benzene by mole at different temperature, which is the room temperature. Okay, so 2 things are coming into our mixer. So stream 1, stream 2, let's call this C. Pure benzene. B, 20% benzene mixture. So this is with propanol, right? So for this guy, I have the mole, basically the number of moles coming in per second is 10 mole per second. So I will call it N dot A. N dot B, which is the number of the moles in stream B per second, is 30 moles and we would like to see if this mixing is happening in an adiabatic fashion. What would be the final temperature of the mixture leaving the mixing point? Okay, so that's our goal, to find what is the T temperature of the basically this outlet stream that we have. So where do you start? What are the tools in your toolbox here? You know the conservation of mass. What else we know? From Thermo 1, conservation of energy, right? So let's just start with the conservation of mass. Can you tell me what is the number of the moles that getting out? 40, right? So it's just a mole, basically a simple mole balance. So what I'm going to write here, I will write the mass balance here for benzene. So I have 10 mole comes in. It's pure, so it's the mole fraction is 1 from one stream. This is from stream A. Then what? Then I have 30 mole per second comes from the stream B 2. So this is a stream B. Should be 40 times some mole fraction, X1. So component 1 is the benzene. Propanol is the component 2. Okay, so I'm going to call that mole fraction as X1. So I can calculate X1, right? So one equation, one unknown. That's just a simple mass balance. So using this, the X1 becomes 0.4. And obviously X2 is the mole fraction of the 2-propanol in the stream C is what? 0.6, right? So mole fractions, they add up to 1. So X2 is 1 minus X1, so it's going to be 0.6. Okay, good. We need to have more information, right? So I cannot talk about temperature as long as I have something about the energy of the system, pure component, and also the mixture. So in this particular example, what we have also is the curves. Basically, these are the curves that shows the enthalpy of the mixture as a function of the mole fraction of benzene in this benzene to propanol system. Okay, so we have two temperatures at room temperature, that blue color, 298, and another one at 308 Kelvin. So the reference point is set at 298 K. So for pure components, at 298, the enthalpy is set to 0, right? So I'm talking about these 2 points here. These are your reference point. So always when you were calculating enthalpy in term of 1, you were calculating with respect to one reference temperature, right? But just remember for pure component, you had a T2 minus T1, and T1 was your reference point. Always reference point is set at 298 room temperature. That's the convention used. So that's why that blue curve at both sides, both borders, always is at 0. Okay? Then, of course, this mixture that we have is not ideal. Because if it was an ideal mixture, let's say at 298K, what was the curve, basically? Shape of this?
Straight line.
A straight line, right? Straight line. Okay. And another point you need to notice here, for 308 temperature here, the pure component enthalpy are slightly different, right? So one is here, another is here. So this is the, based on our notation that we have adopted in this example, this is H2, this is H1, right? Because benzene, we said this is component 1. Are you comfortable how to read this graph? And whenever you are in the middle of these two borders, you are in the mixture. So that's the mole fraction of the component 1. Okay. So what we are going to write now is the energy balance. So our system, we have another key important information in this problem, right? So the mixing is happening in an adiabatic manner. What does it mean?
There's no heat loss.
There is no heat loss, basically, or basically heat is not lost. There is basically heat transfer is 0 between the system that you have and the surrounding. And system is your mixer. Okay? So I'm going to write the energy balance. Right? This is the basically full-blown version of the energy balance. And now you are going to drop the terms here, right? So do you think you have anything on the left-hand side? The process is at a steady state. So this is the assumption we are going to make. So all the parameters with dt, they are going to go away. So there is nothing here, 0, steady state. We didn't have any mention of changing the elevation or the velocity of the, basically the kinetic part of the energy. So this 2 part also, they go away. There is no shaft work involved in the process. There is no contraction expansion work. And this is the adiabatic part, Q dot equal to 0. Now I can change this problem easily by telling you that the process is not adiabatic. So I'm either going to ask you what is the Q, or I'm going to give you this Q and estimate the temperature. So I can play with that parameter easily. Okay, so if I write it a little bit in a clean way, and I will also, instead of using a specific property, because this is a specific enthalpy, so I will write it in terms of molar enthalpy, right? So for what I'm going to have 0 is going to be equal to n dot A HA. Remember, this is the A stream. It's pure benzene at T308 15K. plus whatever comes from the stream B, enthalpy of that. So this is a mixture at T 298.15. So this is a mixture. Minus, it goes out, basically out of the mixture, right? So remember, mixer is our system. In minus out. So this is N dot C, HC. So this is mixture at an unknown temperature. Are you okay with this? Simple energy balance, right? So that's what we care here. We are not interested in other terms. All right, so let's now think about term by term, right? So do we know anything about this parameter here? So these are the parameters that we need to figure it out, right? Yeah. HA is 0. Why is that? HB is 0. Okay, so that's good. So HB, so it is the basically mixture enthalpy. Don't write it 0. Let's talk about that, right? So it's a mixture enthalpy at 298. Do you have the, okay, let's go here. Maybe it's easier to see. Let's write it here. HB what was the mole fraction over there for component 1? 20%, right? Okay. Now look at the curve again. Is HB 0? So this is at temperature. Let's write it. Oh, sorry, 298, right? Okay. So where I am on this curve, if we would like to identify that point. Mole fraction of benzene, right? So this is X1. 20% here. And I need to look at this curve. So HB is not 0 because it's a mixture. If it was pure, yeah, it was 0. So that's the number we need to basically record for HB for our calculation. So this is going to be 670 joule per mole. HA, so this happens as X1 equal to 1, temperature 308.15. So basically I'm going to look at the black curve, right? So what is that number roughly? Basically show me where it is on the curve. Which part I should look?
Looks like it's about 1400.
Yeah. Mm-hmm. So it's here, right?
Yeah, it's there.
Pure benzene. So that's the important thing, right? Pure benzene, X1 is going to be 1. So I'm going to look at that number. So that's that part, right? So because it was pure. So this value, based on the numbers that I have on my notes, it's 1300. Okay. So how many unknowns do I have here in this equation? So let's go back and look at this equation. Now we know what is HA, right? We know HE, right? So I can use this equation to calculate the enthalpy of the mixture, right? This is whatever comes out of the mixture that I have. So I can use that to calculate HC. That is good. So let's do that. So if I use that, using these two numbers that I read from the graph, so let's call this equation 1. So using 1, HC is going to be 827.5 joule per mole. Okay. All right. So can I estimate the temperature now? And think about that. You have only this information. So you have your HC. You know it's a mixture, right? You know what is the mole fraction, basically fraction of the benzene and 2-propanol in that mixture, and you know the enthalpy of mixture. Can you estimate the temperature? Do some engineering estimation here. You can do that. This doesn't have anything with thermal. What is the mole fraction of the mixer? Basically, what stream coming out? 40%, right? Was it 40%? Yeah. So I'm here, right? So whatever enthalpy curve I'm going to have, it is going to intersect this line I have, right? What is my enthalpy for HC? $800, right? We just calculated 827, right? Where is the 827 on the vertical axis? It is a little bit less, right? So somewhere here, right? That's our C point that we are looking. Can you estimate it now? The temperature is going to be a little bit less than 298, right? So you can do extrapolation here. That's the best estimation, right? So you just think about that. You have your molar H versus temperature. So this is just another way of drawing it. So you have 1 point at 308. It is here. I have another point at 298. It is here. Extrapolation means that I'm going to extend this curve, right, until it gets to this HC, which is 827, right? So this is going to be somewhere here. Oops. Yeah.
So, what happened to the temperature? Because my brain is saying, wait, you mixed two things and got a temperature lower than both of them?
Yeah. Mm-hmm.
So what is the energy?
Because you are doing it in an adiabatic, basically, fashion. Your temperature can change and can go down. Yeah. So your basically HC. So using this, it's just going to be a slightly change in the temperature. It's going to be 295 K if you use this. And this happens because it's an adiabatic, right? So Q dot is 0. So that's the basically constraint that we put. Okay, so let's talk a little bit about this property of mixing. So far what you have learned is the ideal properties, and also we basically showed that how you can define it for a mixture, that's fine, and your excess properties that shows the difference between the real and pure components, right? So that's the main thing. Now let's define another property. We call this as a mixing property. It can be defined for any property again. volume enthalpy. And basically this characterizes the property of real mixture minus property of the individual component that you have. So let's write it for binary mixtures that we are considering in this class mostly. So binary mixtures means that I have two components. So if I write delta V means that V of my mixture minus x1 v1 plus x2 v2. And remember, for volume, basically we can define this as the V ideal. So the excess property and the mixing property might be the same. So we can define this for enthalpy, same way. Again, this part is H ideal. And for entropy, S2. So that's the main thing that we're going to discuss in the next class. So the mixing property shows the difference between the real mixture value with basically when we are subtracting from the individual components separately. Right? For volume, enthalpy, internal energy, the second part of it, it coincides with the ideal definition. But for entropy, it doesn't, and you will see why it doesn't happen. Okay? So for entropy, it's become more interesting. So for basic, if you think about this, this is the individual entropy of component 1 and 2. Okay? So that's the definition. You will see why we are basically distinguishing between these two type of properties. So if I summarize it here, so for enthalpy, internal energy, for volume, so this is a very nice table in your book. So for the ideal solution, you're just going to sum them up based on your pure component, right? Molar property of your pure component. So if you think about if your mixture is an ideal solution, your mixing property is going to be 0, right? Obviously it's going to be 0 because your excess thing is going to be exactly the same as that definition. You can also, for a real mixture, you can define this excess, right? So that's how you can calculate that becomes 0. But I excluded the entropy here because entropy is going to be very different for these two cases. If you're interested, basically ideal mixture versus just the summation of the pure component. Okay? So we'll talk about that in the next class. See you on Thursday.
Doing the homework, I had some parts I was confused over.
Mm-hmm.
So I noticed your office hours were Monday, which, well,
won't work for obvious reasons. So is there any other times where you're...
Were you in the class at the beginning of the lecture?
So show up early or?
No. Were you in the class in the beginning of this lecture?
I got. I took a wrong turn and showed up
all right.
5 minutes late.
So I will have an office hour on Wednesday at 7 p.m. on our Teams channel.
Okay.
So that's one option. I can meet you also in my office tomorrow. So let me see my schedule for tomorrow. After 1 p.m. until 3 p.m. if it works.
Okay. Thank you.
Yeah. You know where is my office? Second floor of this building, 219. Okay?
Yeah. Well,
So 7 p.m. also on Teams. So which one of you is your...
I just had a club meeting at 7, so I'll just have to miss it.
So does 1 p.m. work for you or no?
I have classes during that too.
So when are you free? So I have 2 defense tomorrow, two PhD defense tomorrow. Tell me the time that works for you.
Well, anytime after. So I have club meetings from 8 to 10 on Tuesday, Thursday, and 7 to like 9-ish on Wednesday.
Are you around at 5 p.m.? Can you stop by 5 p.m.?
Yes.
To 5 p.m. Let's do it.
Thank you very much. Sorry for the trouble.
And then you have to fill the testing agreement.
Yes, I'm going to do that because we changed the classroom,
Yeah.
so I wanted to make sure that it is already reflected over there. So I will do it today afternoon. Thank you very much. Can I help you?
No.
Oh, okay.
My computer's not updated.
Oh, yeah, that's
Does it
okay.
need updating?
No, that's okay.
It was like,
All right, Dave. What?
you have to wait on the computer over here.
See you.